All right, so last time we learned how to work with combinations of capacitors, right? There are two different fundamental ways to connect capacitors, parallel and series. We derived the theory for each combination, and then we use them to simplify a complicated circuit with many capacitors, right? Some of them in parallel, some of them in series. The idea, again, the best way is always draw these diagrams out, okay? Don't do everything on the original diagram, okay? Draw them out, and then if you want to find the equivalent capacitors, you go this way, right? You simplify each diagram until you reach the final one with only one CEQ. And then if the problem asks you to find the information of a single element, okay, you go backwards, okay? You use each diagram to find all the information on that diagram. You use that diagram, that information to help you find the information in the previous one, okay, until you have reached the element you wanted to figure out, okay? That's the right way to do that, okay? Always draw these diagrams, always solve that problem in steps, okay? Don't do everything on the original diagram, okay? So that's what we did last time, okay? We finished that. Now we want to talk about the energy in the capacitor, right? Because as I said earlier, the use of capacitor is to store electric charge and electric potential energy, right? We know it's going to store electric charge, right? Because once you charge the two plates, those charges are going to stay there, right? So the energy, there is an equation to calculate the energy stored in the capacitor. We're not going to derive that. You're going to use integral to do that, okay? We're just going to use the conclusion, okay? So the conclusion is this. The energy stored in the capacitor, potential energy, electric potential energy, it's going to be calculated as the charge squared and divided by 2C, okay? Again, this is not intuitive at all, right? There's no way I can explain how you get Q squared at the top, 2C at the bottom. It's math, okay? You have to do the derivation using calculus, okay? But in this class, we're just gonna use the conclusion, okay? Not everything is intuitive. A lot of things are not intuitive in physics, okay? So, and then you can actually using the relation between Q and V, CQ and V, you can rewrite this in different forms. But again, there's only one equation, right? You don't need to remember there are like different equations. For example, I can do this. I can put 1Q and C together, right? So I can get another form, 1/2 Q times V, right? Because this is just V. Or I can do this, right? I can write this Q as CV squared. And then this is going to give me C squared, V squared over C. So that's going to be another form, 1/2 C V squared. So these three forms, they're equivalent, right? You don't get three equations. But if you read different books, different resources, you may see different forms, okay? But they're the same equation. They're equivalent. They're totally equivalent, okay? You don't need to remember like different equations. And this equation is going to be given on the test if I want you to find the energy, okay? So, and then this is the general equation for any capacitor. Again, we can derive a very nice equation for parallel plate capacitors, right? All we need to do is just use the C equation, epsilon naught A times D, and then also the this equation, the V equals E times D, right? If it's parallel plate capacitor, the electric field is going to be very uniform, right? So if I start with this form, let's start with this form. That's a little bit easier because we have an expression for C, expression for V. So for parallel plate capacitor, you would have UC equals 1/2. Let's put the expression of C in. And then I'm going to square this thing which is going to give me E squared, D squared, right? And then I'm going to cancel 1 power of D here. So what do I get at the end? I will get 1/2 epsilon naught A times D and then E squared. Okay? Why do I put A and D together? Okay? So because if you realize that if I have 2 parallel plates, right? And then I do the A times D, A is this area, right? D is the distance between them. I actually just get the volume between them, the volume, the space between them, right? A times D, okay? So we can use this conclusion to define another thing called electric field energy density, okay? So this is energy, this is big U. We use another thing, little u, okay? So some people, they get confused, okay? This is the density. Little u, we use the subtrate E because this is going to be a general conclusion divided by the volume, okay? Because if you do the energy divided by volume using this conclusion, okay, you're just going to get 1/2 epsilon naught A times D E squared divided by the volume between them is just going to be A times D, right? Cancel out, so you get 1/2 epsilon naught E squared, which is a very nice equation. That's the density, electric field energy density, okay? So even in vacuum, an electric field carries energy. You can calculate the energy density of the electric field, right? There's a whole region. You can calculate the electric field energy density. If it's uniform, you can use this to multiply this by the volume. You can get the total energy. Okay, so electric field carries energy, okay? And that is why energy can be transported by EM waves, right? And think about it, microwaves. Microwaves have energy. That's why you can use it to heat your food. Okay, if it doesn't carry energy, where does this heat come from? Okay, so even though we derive this using parallel plate capacitor, this is actually a general conclusion for any electric field. Okay, you can always calculate the electric field energy density using this equation, right? Because you see that the only thing you need is going to be the electric field at that point. Okay, this is going to be a constant. Of course, if electric field is not a constant, right? If you have an electric field like this, right? So the strength of the electric field at every point is going to be varying. It's not going to be the same. So the density, electric field density, is going to be different at every point. And that's not a surprise, right? We have things changing around us, right? It's actually hard to find constant things in our real life, okay? So if you see things changing, that's actually normal, right? If you see things constant, don't change, that's actually very surprising in real life, okay? So that's the, but just don't get these two things confused. This is the energy in a capacitor, okay? The total energy is stored in the capacitor. This is called energy density, right? So the unit of this guy is just going to be joules per cubic meters, right? It's going to be joules per cubic meters, okay? Now let's take a look at an example. So in this example, as I said, the use of capacitor is to store electric charge and electric energy. And then the C is a measure of this, the ability of this capacitor to store electric charge and electric potential energy. So in order to have it to store as more as possible, we want to make sure the C is as large as possible, right? So that's why we put dielectrics in this capacitors to make sure the C gets larger, the Q, the maximum charge, gets larger, and also at the same time, it's going to make the breakdown voltage higher, which is also good. And at the same time, actually, it's going to make sure that the electric field energy it can store is going to get larger, and which is not a surprise because everything is going to get larger, right? Okay, so now we're going to see a problem. Okay, it's always easy to understand the theories with numbers. So we can see how adding these dielectrics can increase the electric field energy a capacitor can store. Now let's take a look at this question. 2 3 centimeter diameter aluminum electrodes. Okay, so this is the same capacitors we have seen at the end of PowerPoint 7. Okay, so so that means we can use some numbers from that PowerPoint. Okay, but let's take a look at it. I want to find the maximum electric field energy this capacitor can store. Okay, so the maximum electric field energy this capacitor can store, I'm just going to use this equation, right? This is the energy it stores, but how do I find the maximum energy it can store? Well, you just make the charge maximum, right? Remember, the C is a property, C is a constant for the this specific capacitor, okay? So the U max is just going to be Q max 2C squared. And we have found these two numbers in PowerPoint 7, right? Excuse me. So that's the C we found, okay? It's actually 1.25 times 10 to the negative 11 farad, okay? You can also check your notes. And the Q max we found, right? How did we find Q max? You still remember that? We just did C times V max. And V max is just going to be E max times D. And that's the dielectric strength. That's a property of a certain material, right? For air, we looked it up and then put it in, find everything. So the maximum charge we found in that part is 1.875 times 10 to the negative 8 coulombs, right? Okay, all you need to do is just put these two numbers in that equation. You can find the maximum energy the capacitor can store if there's no dielectrics between them, only air between them, okay? Pause the video, do this. This is an easy one, okay? Now you can find this is going to be 1.41 times 10 to the negative 50 joules, right? So that's when there's nothing between them, okay? Now what we're going to do is that let's take a look at the same capacitor if I put dielectrics between them, like Teflon, like what we did last time. If you put Teflon between them, we still want to calculate the U max, the maximum energy it can store, and then we're going to compare that with this number, okay? So for the electric field energy, okay, and parallel plate capacitor with dielectrics, you can repeat the same process, you will get the same equation, right? So, but the density, electric field density is going to be different, okay? For the only difference for capacitor, but we're not going to calculate, I don't think we're going to calculate density here. But for the field energy density, the only difference is this, right? So this is the energy density. You can see the duration on this slide, 1/2 epsilon naught E squared, and then with dielectrics, the only difference is then you're going to get a K, effective K, the dielectric constant, and this equation. But this equation is still the same, right? Q is the Q max, C is the new C, okay? So you can calculate the new C, okay? Now let's take a look at the slide 11. So that's still the same capacitor we discussed at the end of PowerPoint 7, right? The last slide. Now if you put Teflon, field Teflon in the space between these two parallel plates, what we found is that you're going to still find the C, which is going to be K times the C naught, which is this number, right? And the K for Teflon is 2.1, right? I believe that's what we used. Yes? And then Qmax, we did that, right? It's going to be K times C naught, again times Vmax. But now the Vmax is going to be the Emax for Teflon times D, right? So we found these two numbers, right? So the Qmax we found last time was 7.875 times 10 to the negative 7th coulombs. Okay. Now, if you want to find Umax, you're going to do Qmax over this 2C. But again, this 2C is going to be the original C multiplied by this dielectric constant, right? Now I can pause the video and find the C. I'll find the maximum energy. Okay, so the energy I found, I put all the numbers in. All right, so if you divide them, okay, you see this is what you get when you have Teflon, right? If you divide them, what do you get? Okay, you get about 800. Almost 800, okay? So by putting Teflon between these two electrodes, you can increase the maximum electric field energy stored in this capacitor by more than 800 times. That's the point. That's the reason for dielectrics. It's going to increase everything we want, okay? All right, so we have finished all the theories. Now I'm going to tell you some applications of capacitors. So again, capacitors are widely used in our life. It's just a lot of people don't realize that. Okay, don't know that. For example, the flashlight. Okay, the flashlight on a camera. Okay, where does that come from? That's just the energy released in the capacitor inside this camera, okay? So when you take a photo, when you tell your phone that I'm going to take a photo, okay, it's going to quickly charge the capacitor. And then when you take the photo, okay, it's going to quickly release the energy in this energy stored in this capacitor in the form of light. So that's why you see a flashlight, okay? So it's a very quick release of the energy stored in this capacitor. So that's what we mean by I'm going to store the electric charge and energy for later use, right? This process is really quick. It's going to quickly charge the capacitor. It's going to quickly discharge and release this capacitor. But still, right, you're going to first store the energy and charge and then release the energy in the form of flashlight so that you can take a picture, okay? So that's a very important application of flashlight. Capacitors, right? Another one, okay, is this one, right? It's this defibrillator, okay? I'm sure that you have seen that in movies, okay? And if you're going to become doctor, some of you might, even use that, okay? So what's the use of a defibrillator, right? The defibrillator, the doctors use a defibrillator to send a very strong electric shock, okay, to the chest of the patient in order to bring the heart back to its normal rhythm, right? When the heart is failing, right, you have to help the heart to go back to its normal rhythm, right? So how do you deliver that very quick electric shock, right? You use these two pads, and these are parallel plates, right? So what the doctor is going to do is that the doctor is going to charge these two plates, right? And then place them on the chest of this patient. So in that case, because human body is a conductor, right? So the chest is going to provide a path for these charges to discharge, to find each other and get neutralized, and then send out the energy, right? So release the energy stored in this capacitor. Now you see that the energy is going to become a very strong electric shock. Okay, and then if you have seen that in the movie, right? They place the doctor is going to place the pads on the chest of the patient. Then you're going to see a sudden shock, and then that's it, right? It's only going to send one shock, and then the doctor is going to lift these two pads and then charge them again, right? And then he's going to release the energy as an electric shock. Okay, so you see that capacitors, they can even save lives. They can even save lives. Don't say physics is useless. Don't hate physics. You don't have to be a physicist. Okay, you don't have to be a scientist, but you should always appreciate that. Okay, science, physics has definitely made our lives better, and they can even save lives in this case. Okay, another application is the keyboard. Okay, so when you type on a keyboard, okay, how does the computer know like which key you're typing, right? How does it detect? Okay, again, it's a parallel plate capacitor underneath each key. Take a look at the image, right? So there are two plates underneath this key. So when you type this key, so you're compressing the distance between them, right? So when you do that, and I know that C equals epsilon naught times A divided by D, right? So you're reducing the distance between these two plates. The C is going to get larger, right? If the C is going to larger, so say these two plates, they have a certain voltage on these two plates. So the charge on this plate, if this guy gets larger, the charge is going to get larger. Right? So there's going to be some charge moving really quickly underneath this key every time you type it. Right? So every time you type it, you send out a signal to a very, very short current, okay? A very, very short current to the computer. So the computer knows you're typing this letter, okay? So that's how it detects the signal, okay, when you're typing its capacitor. Isn't that nice? Okay. Okay. So another thing, still your phone, okay? The touch screen, okay? Now I know that everyone uses a smartphone, okay? You probably have heard about this capacitive touch screen. That's the material used on touch screen, okay? The idea of a capacitive touch screen is the same as the, it's still capacitors, okay? It's still capacitors. So basically there are different layers on the screen. Okay, you can see that, okay, because it's very tiny, okay. There are very, very thin layers, okay. So normally there will be some charges on these layers. And when you touch the screen, okay, when you touch the screen, again, human body is a conductor, right? Your finger is going to conduct some charges, okay. So in that case, again, you disturb the balance of these charges. So some charge is going to be moving, okay, to restore the balance. So that's how the screen detects where you're touching, okay. And it has to be very sensitive, right? Even a very short amount of charge, okay, it can detect, and it has to be very accurate. It can detect where you're touching, okay. So there's a lot of capacitors on a smartphone, okay. And the number of capacitors in a typical smartphone, over 700. Okay, you see that capacitors, they're widely used in everyday life. It's just a lot of people don't know that, right? There are so many capacitors in your cell phone, so don't ever say physics is useless, okay? Don't hate this stuff. You don't need to understand this stuff to use a smartphone, right? But you should always be grateful. You should always appreciate the theories discovered by these smart physicists, these great minds in human history. Without them, you can imagine our life without them, okay? All right, so we have finished this part. Now let's move on to the next part, okay? So now we're gonna start a new topic, electric charges, okay? So electric charge and resistors and voltage. So I hope this part is very straightforward, because I believe everyone is familiar with these concepts: electric charge, electric current, resistor, and then voltage and power and things like that. So that's what we're going to do, okay, in this part. So we have seen that if you use capacitors, right, you can store charge and energy, you can quickly release them, right? But you only get a very short current, right? You will get a very short electric current, okay, discharge, okay? But if you want to have a continuous current, like all these lights, right, you want the current, you don't want a short current, right? You want a continuous current, right? So you're gonna make an electric circuit, okay? So you're gonna make sure there's always a potential difference in the circuit to move these electric charges, okay, to continue moving this, move these charges continuously in this loop. So first of all, you need to have a closed loop so that they can continuously move in this circle, right? And then secondly, you're going to make sure there's always some potential difference of voltage to drive them, right? If there's a voltage, there's a potential difference, there's always a force in the circuit, right? Electric force, okay? So it can drive this electric charge moving in this circuit continuously, okay? So that's what you need to make a continuous electric current. You need a closed circuit, you also need a voltage source or potential difference source. So a battery is a normal voltage source. What it does, so it's pretty much like a charge pump. It pumps charge from low potential to high potential, right? Why? So because the charge, think about if the charge is the current goes from the positive terminal to negative terminal, right? If nothing brings them back from negative to positive, they're going to stop there, right? Because the negative terminal is lower than positive terminal. So imagine currents like water, right? It flows from high potential to low potential, right? So the battery, what the battery does is then it's going to pump it up to higher potential, and then it's going to continue moving to a negative potential, negative terminal, and then pumped up again. So, okay, so that's the cycle. Where does this energy come from? It comes with chemical energy stored in the battery. Okay, so conservation of energy. See, everything is consistent in physics, everything. Okay, now let's define something, okay? If we want to make predictions, we want to do experiments, we need theories, we need equations to make predictions. We can't do things intuitively, okay? If you do things intuitively, that's very limited amount of things you can do, okay? You're going to be very, very limited, okay? So the current is defined as that if there's some charges flowing in a conductor, right? So we define, this is a definition, as the time rate of flow of electric charge through the cross-section area of this conductor, okay? So it's always defined as the charge moving divided by time, okay? And of course, if you want to find instantaneous current, you take the derivative of this charge with respect to time. Okay, and the unit, well, that's easy to see, right? Coulombs per second. And then we do have a new name for it, we call it amp. Okay, in honor of ampere. So that's the definition of current. Okay, now I want you to practice this definition using this question on slide 3, okay? So 7.5 times 10 to the 14th electrons flow through a transistor in 8 milliseconds. What is the current through this transistor? Okay, how do you find the current? Well, use the definition, right? The amount of charge divided by the time for this charge to flow, okay? So in this case, the time is given, converted to SI units. The problem doesn't give you the charge, okay? The problem only tells you there are so many electrons flowing through this transistor in that amount of time. If you want to find the charge of these protons, right, you're going to do this. The number of these electrons, right? No, not protons, electrons. Times the amount of a charge each electron carries, right? It's like there's 50 people here, right? Everyone carries like $1, like $10. What is the total money in this room? You're just going to multiply the number of people and the money each one has, right? So you shouldn't just do the number of electrons divided by the time. You're going to get a ridiculous number, right? You're not going to get that huge current. That's going to damage everything. Okay, now you can pause the video and then find the current. All right, so if you put everything in this charge, the charge and electron carries this. Okay, you put everything together And when we define current, it's always positive, right? That's why we use the absolute value there. So the current in this case, it's going to be 0.015 amps. Okay, so that's a reasonable number for a transistor. Okay. All right. So, and we know that some materials, they're good at conducting current. Some materials, they are not, right? So what measures the how good material at conducting current? That's called resistance, right? So resistance is the measure of the opposition to the flow of current. Because when this current, a current is just a lot of charges flowing in the material, right? When the charges are flowing, they're constantly colliding with other particles in this material, right? So it's sort of like some friction, right? In some material, this friction is very small, so they have very low resistance, right? Some materials, the friction is really large, so there's a large resistance, okay? So that's the definition of resistance. And then how do we calculate the resistance of a certain material? That's the equation. So this rho is the resistivity. It's called the resistivity. Again, it's a property of a certain material. So you can look it up. They have been determined experimentally. And the L is the length of the material. And A is the cross-sectional area of the material. So this guy has a unit. I'm sure that everyone knows that. We call it ohm. Okay? And the symbol, we use this Greek letter, omega. Okay? So then this rho actually has a unit ohm times meter, right? Because you're going to make sure when you multiply all these three units together, you get ohms on the left. So this guy must be in ohms times meters. So take a look at the table of resistivities on slide 5, right? So you can see that pretty much all metals have very, very low resistivities. That's why they can conduct current very easily. We usually use metals to conduct current, right? Take a look at like glass or rubber. The resistivity is huge, ridiculous, right? 10 to the 10th to 10 to the 14th, 10 to the 13th. That means they're going to have, if you use them to conduct current, they're going to give you a very, very large resistor. So pretty much they don't conduct the current, right? You're not going to use it like a glass to conduct current, right? And then if you take a look at a silicon, silicon is something in between, right? It's 2 times 3 times 10 to the 3rd. So it is large. It's not as good as the metals, but it's not as bad as this glass and rubber. So that's something in between, right? So that's why we have these 3 names for these materials, okay? For materials that have a very low resistivity, so they can conduct the current very easily, we call them conductors, right? I'm sure that people are familiar with this name. For materials that don't conduct electricity very well, because they have a very high resistivity, very ridiculous resistivity, we call them insulators. And for something between like a silicon, we call them semiconductors, okay? And the resistivity of silicon actually can change under different conditions. So that's why they can behave like a switch. They can represent 0 and 1, right? In electronics, that's why silicon is widely used in electronics, computers and stuff, okay? All right, so that's that. Now I want you to practice this definition again using this question on slide 7, okay? Pencil lead is actually carbon, okay? I want you to find out the resistance of this pencil lead using the diameter 0.05 centimeters and the length 6.4 centimeters, okay? So in order to find the resistance, I'm going to need the rho, L, and A. L is given, right, converted to SI units. A is going to be pi r squared, right? It's a circle. Rho, so let's look up this resistivity of carbon. Carbon is here. You can take a look at the table on slide 5. So that's going to be 3.5 times 10 to negative fifth. So this is still, carbon is still a very good conductor, okay? All right, you put everything together, you can find the resistance, okay? So I can pause the video, finish the algebra. This is pi r squared, okay? The answer I got, what is your answer you got? 11.4 ohms, right? Remember to divide the diameter by 2 to get the radius. So that's the typical value, okay, for pencil lead, okay? All right, so that's the resistance, okay? And then what's the relation between the current, resistance? That's a very famous law, okay, as famous as Newton's second law, Ohm's law, right? So Ohm's law is actually an empirical law. It's not a fundamental law in physics, okay? Only certain materials obey Ohm's law in certain conditions, okay? So it's not actually, but it's a very useful empirical law, okay? It can give us very accurate results in macroscopic scale, okay? In a physical system. So Ohm's law is this. So actually, the relation between the current, resistance, and the voltage is very simple. It's linear. Okay, the current just is equal to the voltage divided by the resistance. So if you compare it to Newton's second law, right? So the voltage is just the driving force, right? It drives the current, right? And the resistance, the material provides some friction, or you can think of it as the inertia of this material, right? So the current is the result. Okay, it's very similar to the relation between these three guys. Okay, so that's the relation between them. Okay, again, I believe most people are very familiar with this law. Now let's take a look at a very simple circuit. Question on slide 9. Slide 9. A 15 centimeter long copper wire. Copper wire is widely used to conduct the current, right? It's a very good conductor. Has a radius 0.225 centimeters. It's connected to a 3-volt battery. What is the current in the wire? Okay, so if you only connect a copper wire to a 3-volt battery, okay. So if you want to find the current, okay, you're gonna do this, and the voltage is given. Right, the voltage in the problem is 3 volts. Now, then you need to find the resistance, right? Well, the resistance, you can use this equation. So it's still going to be rho length times pi r squared. So the length is given, the radius given, so you don't need to divide it by 2. Convert everything to SI units. Look up find the resistivity of copper. It's 1.7 times 10 to the negative 8 ohms meters. Okay, so use your calculator, put these numbers in very carefully, find the current for me. So this number I found, it's 18750 amps. This is a ridiculous current, right? If you have this current in the circuit, it's going to damage everything. Everything is going to be gone, okay? So this is what's called short circuit, right? I'm sure that everyone knows that, because you shouldn't short circuit anything, okay? A short circuit is just a circuit that only has like conducting wires or something with very, very small resistance connected to a voltage source. So it's going to generate a huge current in this path, right? So it's going to damage everything in this path, okay? So the reason is because if you connect the conducting wire to a battery, right, it's going to definitely damage this battery. The battery is going to be damaged, right? Okay, so you should never do that. You should never short circuit anything. Okay, so that's okay? Now, okay, so let's take a look at the next question. The conducting path, so we want to find a safe voltage for a human. Okay, so that's what we want to do. The conducting path between the right hand and the left hand can be modeled as a 12 centimeter diameter. You see diameter, you're going to divide it by 2 to get the radius. 175 centimeter long cylinder. The average resistor of the interior of the human body is 5.4 ohms meters. What voltage between the hands is needed for lethal shock of 110 milliamps? Okay, so actually the current a human body can take is actually very small. Okay, you see that a current of about 100 milliamps is going to kill you. Okay, so and then we want to calculate the safe voltage, okay, to a human. So if I want to find a voltage, right, so I'm just going to rearrange this equation. I times R, right? So this I is given, right? We're just going to use this maximum. This is the maximum voltage we can take, a human body can take. You convert it to amps, that's 0.11 amps, right? So if you want to find the maximum voltage, the safe voltage for human, that's the maximum voltage that a human can take before we die, okay? And then, again, you just combine this with the resistance equation, right? The rho is given, the length is given, the radius is given. No, this is not R. Pi R squared. So you put everything in, okay, what is your answer? Okay, so my answer is 92 volts. Okay, so you see that the voltage a human body can take, okay, it's very, very low. It's like lower than 100 volts, okay? So what is the voltage you get from the wall outlet in this country? Okay, that's 120, I believe. Okay, if you go to China, the voltage from all these wall outlets is going to be 220. Okay, so so that's actually very dangerous to us. It doesn't matter if you're in the U.S. or in China. Okay, you should never use your bare hands to work with these wall outlets, especially when your hands are wet. You never do that. Okay, that's what we are told when we're kids. Okay, that's because they can definitely kill us. Okay, that voltage can definitely kill us. All right, so that's pretty much everything I want to tell you in this video. I'm going to stop here.